All right. So in this talk, I want to talk about how we designed our upcoming model that is a small agentic model. And I want to do it not only from a training point of view, but also from a harness point of view. So hopefully you will find this presentation useful with a comprehensive approach from architecture design to downstream application. Okay, let's start with a simple question. Why are we interested in edge models at all? If you look at the headlines, I think frontier, really big models are really the most popular ones, but edge models have a lot to offer. And the first thing is cost, because the tokens are free. You do not pay an API token here. You just care about the inference on your own device. So basically, the tokens are free to generate. A second thing that is very interesting is the latency. Because it's hosted locally, it means that you don't have the latency of a remote model. Plus, these models are small, so usually they're also faster by design. The third thing is connectivity. With API models, you cannot really power applications that cannot rely on a stable connection. So, for example, you can think about automotive applications. This is very risky to rely on a stable internet connections here. And the last one is privacy. Because your data never leaves the device, it's always private, and you don't have to worry about what you share with the model. Everything stays private. All these properties are very nice, but it also comes with three major challenges that I want to talk about now. So the first one is that it must fit on a phone, and that can be quite difficult because it means that the memory usage that you have is very limited. So it will constrain the size of your models, which is why edge models are typically very small. The second thing is that it must be very fast. If you run this on a device like a phone or like an old CPU, basically most of the deployment scenarios involve um, more like low-end hardware resources. It involves a lot of CPU. So you need to have a model that runs fast, mostly on CPU. And the final thing is that it must be great at agentic task if you want to use it for this purpose. So if you want to summarize these three challenges, the first one is about memory usage. The second one is about inference speed. And the third one is about quality. And we want to make sure that we maximize this triangle and we optimize the model from the architecture design to the training and downstream deployment to make sure that everything is as good as possible. So let's start with the architecture. And by architecture, I want to talk about mostly the layers that are used inside of the model from a inference speed point of view mostly. So let's take two models, Gemma 3270M and Qwen 3.50.8b. And you can see that they both have a hybrid architecture where they interleave some kind of attention with another type of layer. So basically, you want to have something like full attention, like GQA, to have recall and be able to remember all the past context inside of your input. But you also want to interleave it with some kind of efficient layer, like sliding window attention, so it's not too expensive to run. So both of them run this kind of hybrid architecture, and both of them are a really good architecture. They're very fast. The problem that you see if you dive a bit deeper into the embedding layer is that they're very big. Basically, the vocabulary size of the tokenizer is huge for such small models, which means that the embedding layer is most of the model for Gemma 3270M. And that's an issue. It's probably due to distillation. They train these models by distilling them from bigger models, which is why they have these huge vocab sizes. But it means that in practice, the effective size of these models is very small. If you look at Gemma 3, it's mostly 100 million parameters that are actually used for reasoning and not just for embedding. And for Quen 3.5, it's about 600 million parameters. So that means that the model will have fewer parameters to reason with, and it means that the quality will suffer. So when we design our model, we try to take it with a small vocab size to make sure that the effective size is pretty much in line with the total number of parameters. Here you can see it's about 90% of the model params. And we created a particular layer that we interleave with GQA, which is this short conv layer. And to design this short conv layer, what we did is that we really evaluated it on device with real hardware doing profiling in loop. And we really monitored the inference metrics that this layer would provide us. So here are two hardware targets that we optimize the model for. And with this inference metrics, we had like real signal because there's often a gap between the theoretical gains that you have from a layer and the practical ones where it can be a lot worse than you imagined, which is why this on-device profiling was really essential here. And here you can see a representation of this short conv, also called gated short convolution block. And if you want more information about this, we have a LFM2 technical report online, so you can find all the relevant information about how it was designed. But I want to talk about the gains that we have here, and you can see on the left the short conv layer and the cost of each or other layers. So you can see that on this M4 Max CPU for decode speed, it's pretty much twice as efficient as GQA, and you can compare it with the other layer types that we saw for Gemma and Quen. So we really optimize it for speed, and this is something that you see if you really benchmark the model with CPU inference metrics, here with prefill, decode, but also memory. And you can see that compared to similar sized models, it is a lot faster, not only on CPU, but also on GPU. Here you can see it with different levels of concurrency as well. All right, that's it for the architecture side. As you can see here, we talked about the size of the model, which corresponds to the memory usage. And we also talked about the inference metrics because we wanted the model to be fast, to be really deployable on device. This is particularly true if you have an agentic model that needs to handle long context and also be very responsive because that's what people are used to. Let's now talk about the quality aspect of it. So this is mostly about post-training. And if we look at the post-training history, the timeline, you can see that we had the dark ages with the SFT era where post-training was basically supervised fine-tuning. And we have like a key papers and releases from this year. And then we had the policy optimization, the XPO era, with a lot of papers published about direct preference optimization and a lot of different flavors of it. So that was nice. And then DeepSeek R1 made a big splash about the reinforcement learning with verifiable rewards strategies that you can take. And this era is already over because we started a new one. And this new one is about multi-domain on-policy distillation, or MOPD. And this is what we're going to talk about here. So this is our training recipe at Liquid for upcoming 2.6B model. We use multi-domain on-policy distillation with agentic reinforcement learning. And you can see the top row is about how we train the specialists, the teachers. So instead of training the model directly on math, knowledge, code, etc., we train some teachers on them. And then we merge everything into one single student, you can see at the bottom, with multi-domain on policy distillation. Then we add agentic reinforcement learning because we want to make sure that this model is really good at using agentic harnesses, and that is how we got the final model. So let's talk a bit about SFT. SFT is mostly about how you curate a lot of high quality samples, which is something that is often overlooked. And in this presentation, we will overlook it once again. We will mostly talk about the consequences of SFT and a particular problem, especially, which is doom looping. So here you can see an example of a doom loop. You prompt the model with an instruction, and you can see here that in the answer, we have a lot of repetitive substrings. And this is something that often happens with small models. It also often happens when you have reasoning traces, so when you have a thinking model. And finally, it often happens when you have complex tasks. So when you have a small agentic model, you have all three of them at the same time, which is why doom looping can be a real issue. So at Liquid, we developed a solution for this. We called it anti-doom. And the idea here is that you're going to use a dataset of prompts and you're going to generate answers with your model. And then when it starts doom looping, you're going to look at the token, the first token of the doom loop, and you're going to downsample it. You're going to reject this token and you're going to upsample alternative tokens. So here's an example where you have this generation from the model that is starting, and then after the wait token, it creates a doom loop, which is a very common scenario. So what we do here is we teach the model to reject this particular wait token, and we want it to replace it with let's, yes, or okay tokens. And that is very successful because you can see the doom loop rate going from 10.2% with our model to 1.4%. And even with Quen 3.5 4B, it goes from 22.90% to only 1% of doom loops. So there are other ways of solving this issue or trying to reduce the doom loops. A very common one is repetition penalty, which is a generation parameter that you can add, but it's more like a patch after the model is already released. And here we really want to train the model to refuse doom loops. So I would say that this approach is a lot more robust and you do not need to force users to have very specific generation parameters because the model has been trained not to doom loop. So if you're interested about this technique, we released the code, released the dataset, and we wrote a blog post about it. So everything is available online. All right, let's go back to your training recipe. So we talked a bit about the SFT stage and mostly about the consequences of it. Let's now see the reinforcement learning stage that we use to train our specialist and the MOPD stage that we talked about. So by reinforcement learning here, I'm mostly talking about reinforcement learning with verifiable rewards, which is a very common setting that we saw with DeepSeek R1 and related work. And here you can see a prompt and a answer from the model. And what we do is very simple. We just extract the answer from the response. We have a ground truth answer from the dataset. We compare them and we see if they're correct or not. So that's kind of the general framework, the intuition behind it. A little problem that we see with this is that you only get the signal at the end of the answer. So here we generated 24 tokens and we have only like one bit of signal. This is not really a problem, but if you have super long generations that are multi-turn and are like 100K tokens, this becomes quite inefficient. So a way of making this reward, this signal a bit denser is using on-policy distillation. In on-policy distillation, we still have this answer from the student, But instead of extracting the final answer, what we want to do is that we have this teacher model that does a forward pass and that basically rates each token that the student generated. And it's going to use its own probability distribution for each token to rate them. And you can see here that the first two tokens, fantastic question, have a very high KL. And this is because it's probably slop and the teacher model is not very happy about it. So the teacher model is telling us, no, you shouldn't answer fantastic question to this prompt, and you should probably answer like other tokens at the very beginning. So here you can see that the reward is very dense because we get one piece of signal for every token. So it's so dense that actually it can be a problem. If your teacher is not very well calibrated, it means that it might reject everything. And this is a common problem with on-policy distillation, is that if your teacher is too far away from your student's distribution, it means that it might think that everything the student says is wrong, for example. In this case, if all you get is like, this is a wrong token, this is a wrong token, this is a wrong token, there's not much signal that is created and training can just derail and crash. So now that we talked about this, a natural way of expanding on policy distillation is using several teachers instead of one. And basically, we have different flavors of it, but you can just route each prompt to a particular teacher. So if you have a math question, you can route it to your math teacher. If you have a code question, you can route it to your code teacher, etc., etc. So the idea behind MOPD is that with reinforcement learning with verifiable rewards, we have some degradation that happens. For example, if you train the same model on math, you're going to have writing style that deteriorates. Then you try to do reinforcement learning with human feedback, and then instruction following is going to drop. So each stage kind of fight each other. So it's not very nice, and you keep losing and gaining scores in across different domains. MOPD is a much cleaner approach that ensures that everything kind of rises together and you don't have this problem of fighting different domains. The requirements, as I mentioned, is that the teacher should be very much close to the student, but it should also be significantly better than the student. So usually people assume that, okay, if I have a very good teacher, it doesn't matter. I can just reuse it here and it's going to make my student a lot better. This is not true. This is not enough. This is not sufficient. You also need the teacher to be very close to the student's distribution. Otherwise, you're not going to learn much. And the payoff of this technique is also that it converges very, very quickly. So that's super interesting. And with just like 30 steps, you can basically finish training. So you spend a lot of compute training each teacher, but once they're trained, it's quite efficient to merge them into the same student. And the little thing that I wanted to mention, like based on practical experience, is the reverse KL versus the forward KL. So we have two ways of comparing the output distribution of the student with the teacher. And if you have reverse KL, it's called mode seeking. And I would say I would recommend it if you have many teachers. This is something that works better. And forward KL is mass scoring. So you can see on the graph. It means that it's going to be a lot more covering in terms of distribution. And this is usually better when you have a single teacher because you're not going to have too many different modes. And here I would also recommend using the teacher's top K logits to do it. But there are many, many different flavors of it. And I don't think that we converge toward a single unified solution yet. All right, we talked about MOPD. So the final stage that we have here is what I call agentic reinforcement learning. So this diagram might not be like super accurate, but I think it gives you like a high level of understanding of what we're trying to achieve here. And what we're trying to achieve is we say, okay, models are not consumed as chatbots anymore, and they are consumed through a harness most of the time. Even a chatbot can be thought of as a very, very simple harness, right? So why not, instead of training the model directly, we can train it through a harness. So instead of getting the response from the raw model, you get the response from the model through a harness. And that's very nice because it teaches the models all the built-in tools from these harnesses. It teaches them how to use the system prompt correctly. And if you have seen open close system prompt, for example, it's very, very big. It's over 7,000 tokens, even if it in its most minimalistic form. So it means that it is quite challenging for a small model to really understand everything, and training it directly on it makes sense because it gives the model some understanding of what's in there already, built it in the weight, so it doesn't have to understand it during inference time. Here you can see that we use different harnesses, and the idea is that, okay, I'm going to have a bunch of tasks, um, and I'm going to store them. So in this task, I want to have like realistic productivity things like creating, I don't know, like spreadsheets or a PowerPoint presentation. I want to do some kind of web search. I can design task. And then we're going to give it to the reference model and the policy model here, and they're going to interact directly with the harness in a containerized environment where the model can use a bunch of different tools like web search and come back with the answer. And then we're going to use here, it's like a GRPO setting to calculate the loss and propagate it back to the policy model to train it. So this is the high level intuition behind it and behind what we want to do. Some more practical considerations and lessons from this work is that the reinforcement learning infrastructure matters more than you think. And doing this kind of agentic reinforcement learning is really a stress test of your reinforcement learning infrastructure. So be prepared. Another important lesson is that you really need to properly initialize the model on diverse SFT traces that basically cover a lot of tasks that you want the model to learn. If the model, especially if it's a small model, is not properly initialized during SFT on these agentic traces, it is probably not going to be very good at learning it during agentic RL. So the SFT stage, and this is something that is, as I said before, really overlooked, is it's essential. Like everything that you want to train on, you should have cold start SFT data to properly initialize the model and make sure that you're going to really learn during the reinforcement learning stage. If the task is brand new, if the model has never seen something like this, it's going to be very difficult for it to really get better at it. So that's a lesson that I want to highlight. And finally, training algorithms don't matter too much from our experience. You can see that in the previous slide, I showed GRPO, which is not supposed to be the best performing one in this setting, but it works. DAPO also works. So it doesn't seem to matter too much in this setting. Um, but yeah, that's the big picture around agentic reinforcement learning and the entire training pipeline, how you get your student model, SFT it, train many teachers, merge everything back with MOPD, and then applied a final polish stage with agentic reinforcement learning to make sure that the model that you train is really good at using these harnesses. And speaking of harnesses, I want to talk a bit about it because I think that it's not enough to just train the model now. You really need to have a very close feedback loop with the harness. So we saw it with the reinforcement learning stage during training, but it's also true with the harness itself. Basically, you should adapt your agentic harness to your model and the other way around as much as possible. So I call it model harness co-design, and it's a bunch of very concrete and practical tips and tricks. For example, okay, you have a predictable failure mode. Something that I realized that the model would use bash commands even on Windows, but it should use PowerShell, right? So I can just tell the model, I can just like pass it and detect this failure mode and add a hint to make sure that the model uses PowerShell instead of Bash. This is a very simple way of making the end user experience a lot more consistent and reliable. So why not really? Like the end user will only care if the model managed to achieve the task or not. So that's a nice little trick. Same with tool call parsing. If you have problems with tool call being wrongly passed, you can create fallbacks. You can make it more robust. And that way, you can basically improve the end user experience once again, because this thing doesn't really matter. Like the agentic harness should be able to help the model as much as possible. On the left here in the demo, you can see that we have an agent that spawn other agents to be able to try to book a wedding and organize everything. And you can see that all the agents are trying to do some kind of searches. Here it doesn't have the API key, but it's trying its best. So a bunch of things happen in the background. And this is something that is super interesting because, as I said before, like it's an edge model. So tokens are free here. Like inference is free. It means that you can really token max. You can spend like over 1 million tokens per hour, and that opens a lot of opportunities. So in the next slide, I want to show like a different demo. And in this demo, you can see a 2.6B model powering a little application that has an agent. And in this application, we decided to say like, okay, let's try to have like background agents. We don't want to do something super complex because it's a small model, but we want to be able to just like do triage with your emails, send you a notification when it's needed, digest a newsletter, make a search for you, organize something for you, and be very proactive. Be very template driven. It's easy to spin up an agent. Here you can see that there's a little daily brief, and we have already like a lot of agents trying to take care of things for you during the day. And they are creating a lot of tokens. So here you can see one that is checking if the beach is okay to have a date tonight. And here you can see all the agents and what they've done throughout the day. You can see that they generated a lot of tokens, 27 million tokens. And yeah, that's not really something that you can do with a cloud model today because it's just too expensive. And I think that this is just the beginning, right? I think that, and this is one of the main takeaways that I have, edge agents are not just a compressed version of the cloud API models that we've used. It's essentially a new paradigm. And the idea behind it is that inference is free, so you can generate as many tokens as you want. And it raises a lot of questions that we're currently working on at Liquid, where we're like, okay, like we have the potential of running these agents all the time. How can we use it? How can we exploit it to the fullest? So as you can see, we have these background proactive agents, and we create a lot of them, and we give them a lot of different tasks. And it's okay if they fail because we can have redundancy, we can have some reviews, and that makes the system a lot more robust. So it's really interesting to see how they're going to be used in the future, in my mind, how we're going to change the way we interact with models by having access to these unlimited free tokens. And this is part of like why I think small models are so interesting. They have a lot of unique challenges, like the doom looping that I showed, and many, many others. And I think the way going forward is really to think about agentic harness as an extension of the model, and really co-design them together to make sure that the harness are really useful and help the model support it when needed, to be able to fully exploit it. So that's it for me. Thank you everyone for listening. And I think that we have a bit of QA now.
I'll paste some questions here in the chat so you can see.
All right, yeah, feel free to post your question in the chat if it's not disabled. All right. I see first question. I wanted to know, how do you work on hallucinations? This is an interesting question. So this is not something that I really talk about here in the presentation. But we do have a teacher that is specialized in abstention for the 2.6b model that we're going to release. And here, what we want to do is we want to teach the model to answer when it knows the answer and to not answer when it doesn't know the answer, which is very tricky because, as you know, models tend to be very happy to answer any questions, and they have a poor understanding of their internal knowledge as well. So with MOPD, we actually created a teacher to get better at that. And this is quite successful. A good benchmark to track this, for example, is AA omniscience. All right. Other question, what parameter range is considered edge deployable? It really depends on what you mean by the edge. It has a very loose definition, so it's difficult to see. It can be phone, it can be a lot of different things. I would say that yeah, it's probably under 10 billion parameters. So here you have tiny models with 250M, and that's something that can deploy like really on a tiny chip, but it can go up to 8B, and with 4-bit quantization, you get something like around 4 gigabytes or 5 gigabytes of memory usage, and that's kind of the maximum I would see. But of course, edge can mean many things to different people, so it's kind of loose-ended. Other question, what why is short convolution replacing sliding window attention LFM 2.5? So yeah, it's a good question. You can see here, the main reason is about the cost of each layer, and sliding window attention is a very good layer, but it's still quite costly. It has nice properties, but we decided to go as fast as possible with the LFM2 and 2.5 architecture. So yeah, we just decided to go with an operator that is still quite expressive, but is much faster. All right, next question. Could the idea behind FTPO, so this is the training technique behind anti-doom, could this idea be extended beyond preventing doom loops? For example, to selectively improve hallucination reduction or reasoning quality by optimizing only specific critical tokens instead of entire responses? Yes, this is a very good question. Actually, this idea comes from another paper that we had at Liquid, and this is kind of the idea. Yes, you can use it for many different things. It's very flexible. This anti-doom is just like one use case, but indeed FTPO could be used for this purpose and could be used every time that you're not very happy with the token and you have like a failure mode that you want to fix in a surgical way. So that's a nice approach. I would encourage you to give it a try. All right, next question. Outside of coding agents, where else does reinforcement learning with verifiable reward work? Yeah, coding agent is a good application of it, but you have many other ones. So here you have it with math. Math is a very natural use case for ILVR because you probably know the answer in advance. So that's a nice way of doing it. The abstention mechanism I talked about to prevent hallucination is also another one because you know the answer and you can detect if it's correct or incorrect. So that's another way where you can use verifiable rewards. Tool use is another one. You might know which tool you are supposed to use in a particular context. So yeah, just having it as a ground truth is enough to be able to get better at it. Okay, next question. Is the MOPD sequential distillation from one teacher to the next, or do we interleave teachers? I should probably use this. It can be anything. Basically, it's a very loose name, a naming convention, and different labs have different implementations of it. So it can be everything at the same time. It can be in a sequential way. The MOPD stage can also be divided into like two sequential stages. For example, you might want to do the agentic related domains at the end to make sure the model is really good on it before doing agentic reinforcement learning. So yeah, I would say it's very free form, and there are a lot of tech reports that detail their own implementation. So if you're interested in this topic, I would probably recommend the paper from Xiaomi or Nemotron, DeepSeek V4, or Kimi K3. All right. Next question. I was curious to get your perspective on the best way to get hands-on experience on post-training, especially on low compute budgets. It's an excellent question. This is how I got into post-training, actually. I didn't have the budget to do something like more compute intensive than supervised fine-tuning. So there's a lot of cool work that you can do with very tiny budgets. Post-training is kind of scrappy, and there's a lot of ideas that I think you can try, and they're not too expensive. Of course, if you want to do something like agentic reinforcement learning, it's going to cost a lot because it's a ton of infrastructure, it's a ton of environment. You will need Dockers, you will need like a lot of things that are difficult to orchestrate together. But you can, for example, focus on model merging, which is something that I've done in the past. And model merging, for people who are not aware, is this idea that we can take the weights of different models, same checkpoints, but trained differently. And you can merge them together. So you can just average all the weights. This is called the model soup or linear averaging. And we see that it is a very good regularization factor. It really helps the model when you do that most of the time, and especially in some scenarios, and it can raise performance. So here, I do not mention it in our training recipe, but model merging is something that we do use quite a lot. And that's a great way if you have, for example, many different checkpoints at the end of your agentic reinforcement learning stage here. You might want to upcycle them. And by merging them, you can evaluate it and see like, oh, okay, actually, this makes a mixture that is a lot more balance across different domains. And this is how we got the final model for this specific recipe. So yeah, model merging is a very good one. I think that everything related to evaluation is also super interesting to explore. And finally, data is probably the most overlooked aspect, but also the single most important and high leverage aspect of post-training. So data, yeah, we need more. All right, next question. Can you please suggest a research paper that you would recommend from Liquid AI about its edge LLM architectures? Yes, we have many papers around this, but the one that I would recommend the most is the LFM2 technical report. So this comes from December last year. The LFM 2.5 architecture is still the same, so it's still very relevant. And in this paper, we talk a lot more about the experiments that we did to create this specific architecture. So it's a very interesting read if you are interested in this topic. There's been an increased focus on looped models recently. Has that made its way over to the edge LLM scene yet, or is it still mostly sequential? I think it's still mostly sequential, but it's super interesting. I think looping models. So the idea is that you're going to repeat some layers during inference. It's super interesting because it gives you a lot of flexibility. And here, when we talk about small models, you can see that we actually have a very, very wide range. Here you can see a comparison where we have a 350 million parameter model, but also a 1B model. So it's basically 3 times as big. So there's a huge range in terms of log here. And being able to loop some layers is super interesting because it means that the same model can cover more range. Um, it's still difficult in terms of like latency, maybe if you really want to deploy it on the phone, for example, it's kind of difficult to justify sometimes the trade-off that you can create here. But in general, I think we are going to see more and more looping models on the edge because of this reason. All right. Next question. Were the teacher models also custom trained, or did you use publicly available teacher models? Yeah, this is something I haven't maybe be super clear about. You can see here that all the teachers are initialized from the same SFT checkpoint. So why that? There are 2 main reasons. One is about the tokenizer. If you want to do MOPD, cross tokenizer. So for example, you want to train a LFM model and your teacher is a Quen model, it's not the same tokenizer at all. You're not going to have the same vocabulary at all. And reconciling the two vocabularies, either by switching a tokenizer or by doing like some kind of token surgery, is quite difficult and doesn't work very well in practice. So you can try, but it's very difficult. And the second aspect of it, of why we don't choose publicly available model, is that the output distribution of your teacher should be very close to the output distribution of your student. And here it wouldn't be the case at all. So the teacher might overcorrect the student, and because of that, there's not too much signal that you infer from this. So this is why we really want to use our own teachers. And yeah, from experience, it works a lot better. And this can be even initialized from not just the SFT checkpoint, but different stages in your training pipeline. So this is something that is very robust and very high leverage. All right, next question. As you said, edge models needs a helpful or native harness to work more efficiently, like in your smartphone example. How can I secure the system to not let models go in system configs, etc., and can be edge inference be sandboxed? It's very simple. You control the tools that you give the model. So the model, if you do not give it the tools, it needs to change your systems, your configuration. It's fine. Like it's not going to escape it. It can be sandboxed indeed, but I think the main security layer here is not providing the tools that might be bad for the model to use. And then you can add classifiers on top to make sure that the command that is run or the tool that is used is not harmful in any way. So there are different ways of doing it, but just not giving it access to settings is probably the most robust one. All right. Next question. 28 trillion tokens on 350 million parameter model. Did you hit a hard loss plateau, or is reasoning capacity still scaling linearly? Yes, so for the 350M model that I presented here, we actually overtrain it quite a lot. So if you're familiar with chinchilla scaling laws, it is massively overtrained. Like I don't remember the ratio, but it's something really stupid. You shouldn't be able to, you shouldn't have to use that many tokens to train the model in an optimal way. But we did it nonetheless. And indeed, we did it because we saw that the model still improved. So I think that as long as you have high quality tokens, you can probably keep training. And even at this 28 trillion token limit, the model was still learning. So no, it's not plateauing. You can still add more tokens. And to be fair, this is also what Chinchilla predicts. Like Chinchilla laws predict that it becomes less and less efficient to add more tokens, but it still improves, right? I think what we see is that higher data quality, especially, is a big lift and allows you to really overtrain the model and still see massive gains. So yeah, pre-training can go very far. All right. Next question. What would you say is efficient way to post-train LFM models on Pi harness? In terms of verifiers, what would you say preference for rubrics-based LLM as a judge versus deterministic one like Tokos they are doing? Okay, so a Pi harness. So I'm not sure what you mean by an efficient way of training LFM models on Pi harness, but you can directly like have your agentic reinforcement learning loop and give the model a task and send the task to the model through the Pi harness and check the answer. If the answer is correct, you reward the model. Otherwise, you don't reward the model. So that's the way that we do it with many harnesses. And then in terms of verifiers, you ask the question, okay, like should I use rubrics-based LM as a judge, so having a model reviewing the answer, or should I use something that is more like a hard rule? Like here, it's just a comparison between the final answer that is extracted and the ground truth. It really depends on the domain. You can try to do a bit of both sometimes. For example, with instruction following, you have Python test usually to make sure that the answer that the model generated corresponds to the constraints that you inserted as in the input. But that might not be enough because we see that models can easily reward hack this Python test. And that way you might be tempted to add a judge LLM to not only make sure that the constraints are respected in a very hard way, but also that the answer that the model generated actually makes sense, is actually useful. From experience, when you do that, you realize that the model starts reward hacking the judge LLM. And for example, your model might insert at the end of its response that it is an excellent answer that satisfies all the constraints. And the judge LLM might see that and be biased towards saying like, okay, this is a good answer then. Um, so yeah, there's no very good answer here. I think it really depends on the domain. Something that is more freeform, like creative writing, obviously benefits a lot more from having a particular judge LLM or a reward model. And something more like math doesn't benefit from it very much. All right, next question. How do you know that a teacher is close to the student in terms of distributions? Yeah, so this is what I talked about here with the on-policy distillation. Yeah, it really, it's not easy. You can run some tests. You can like just generate answers and like generate the output distributions with two models and see KL divergence, see how much they overlap. That's a very nice way of doing it. If you've trained the models from the same checkpoint and it's not like pre-training scale, it's probably going to be very close to each other. So here you don't even need to check it. We see in some tech reports, like I believe it's Nemotron Cascade 2, that they had a problem with this. And they have a solution actually, because the student model and the teacher model diverged too much during the post-training pipeline. So what they decided to do is that they decided to generate answers with the teacher models and SFT the student model on them. So they would get closer in terms of distribution. So that's a nice way if you really have this problem to fix it. But it's more like a patch and not ideal, I would say. All right, next question. Is it feasible to predict the expected output length, so the number of tokens of a language model's response before the generation begins, so based solely on the input prompt in question? This is very difficult. I haven't tried to do it, to be fair. I think some domains are naturally a lot more verbose than others. For example, math is super verbose and it's going to generate a lot of tokens. So like on domain basis, you can have like a relatively good average score. Obviously, this is confounded by the presence of doom loops, potentially. If you have doom loops, well, it's going to explode the token generation budget. And the other thing where the other common pattern that we see is that unsuccessful answers produce more tokens on average than successful ones. So it's also going to depend on that. I think this is something that you could try to predict. I think you could even train the model to predict its like internal response budget. Actually co-wrote a paper where this is something that we tried, and I believe it can work. It just depends like on how accurate you want it to be. Okay, next question. How can we combine multiple teachers for the same task? For example, one teacher focused on functional correctness of code and another focused on code security. Yes, that is a completely correct way of doing it. Especially if you want to create a coding model, I think it makes a lot of sense to really have different teachers focus on different things. The same teacher could also provide both signals. It's something that you see that, yeah, it's not necessarily better to have two teachers, but in general, I would say it's probably a good idea to ablate it and do a quick experiment with it. All right, Cohere Labs people, interrupt me if we don't have any more time, but otherwise I will take another question. Is model merging applied to MOEs? Yes, exact same principle. It works very well with MOEs. Nothing to know in particular about this. It just like applies very well to this architecture as well. Next question. Okay, maybe final question. What architectural and design decisions make one AI agent more lightweight than another while maintaining comparable performance and accuracy? I think it's the size of the model. Of course, it's going to be more lightweight if you talk about memory usage here. And the second one is about the KV cache. So if you use full attention, if you use like something like GQA, the KV cache is going to grow quite a lot, right? Based on the input length. So because you have an agentic task, your input length is probably very big. So it's probably going to explode. And if you have something that compresses the input, like short convolution, it's going to be like a fixed length, so it's going to not grow as much. So yeah, that's a way of doing it.